Hello guys, hope you are doing well. In this video I'll be talking about the colligative properties, the section 2 of chapter 1. We will be talking about each of the four colligative properties in detail, and we will be solving questions about each of the colligative properties. At the end of the section we'll be solving several other questions about the section. Guys, the colligative properties in chemistry, we have several properties. You have studied the chemical properties, physical properties, and so on. Each of these properties we define according to the field that they're related with. The colligative properties related to any properties of the solutions, any properties of solutions which changes with the amount of the solute in the solutions. As we add more solute into the solutions, or as we reduce the amount of the solute in the solutions, the colligative property changes. Any property that changes, it can be classified as colligative property. So guys, the colligative properties are those properties which depends on the amount of or concentration of the solutes, not on the identity of the solute. Addition of any amount of the solutes to the solvent, which usually we have water here in our cases, changes some of the property of the solution compared to the solvent, and those properties are classified as colligative property. And we have to know that the colligative properties, they depend on the amount of the solute, not on the identity of the solutes. Regardless to the identity, they changes those properties, the solutes concentration. In our curriculum talks about the four colligative properties, guys. Four colligative properties. The vapor pressure, guys, which reduces by adding solutes. Freezing point reduces as well by adding the solutes. Boiling point with osmotic pressure, they increase by adding solutes. So we have got four colligative properties. Two of them, which are the vapor pressure and freezing point, they decrease or they become lowered value. They will result in lower value when we add more solutes into the solutions. But the other two, boiling point and osmotic pressure, we'll be talking about each of them in detail, guys. Their value increase as we add more solute into the solvent or into the solutions. Let us talk about each of them in detail. The first one is vapor pressure lowering, guys. And the vapor pressure lowering, this lowering refers to what? Refers to it decrease by adding more solute or increasing concentration, molality. But first of all, guys, let us define those solutes that we use or we work with frequently in our solutions. The solutes that we do, they have a property which they do not become gaseous easily, and they do not escape from the solution easily. And those solutes we call as the non-volatile solutes. So a non-volatile substance is a substance which has low tendency to escape to the gaseous phase or to vaporize. The one that has little tendency to become a gas under existing conditions. It says as the liquid or solidus rather than to become a gaseous. And with the non-volatile, we have volatiles as well. The volatiles are those solutes that vaporize easily in the solutions. They have a high tendency to become gas and escape to the surrounding from the aqueous solution. In order to understand the mechanism of the vapor pressure lowering and to compare the solvent or the solution they have lower vapor pressures, first of all, let us define the vapor pressure, guys. The vapor pressure is the pressure caused by molecules in gaseous phase that are in equilibrium with the liquid phases, guys. Suppose here we have a container and the container is sealed container. As a sealed container. And here we have got the water molecules. And we provide heat to this container. We will heat the container. Guys, as we provide heat to the container, the molecules of water escape to the surrounding. They become gaseous. They become gaseous. So they become gaseous. Gaseous. We call this as vapor because the gaseous form of water we call as vapor. And this vapor, guys, when they collect on the surface of a solution or a solvent, the process of evaporating H2O liquid to the H2O gas, we call as evaporation. So this process is what is evaporating or evaporation process. But the opposite process we have as well, we call as the condensation. So there will be another process that the vapor backs to the liquid we call as condensation. There will be, as the molecules in vapor, they exist on the surface, they will condense, and from vapor they become liquid. The vapor pressure is a pressure that exerted by the vapor which collected on a surface of a solvent or solution toward the surface of the solution. So, what are the vapor pressure? The vapor pressure exerted on a surface of a solvent or solution by collected amount of vapor on the surface. And that will be in the position when the evaporation equals the condensation rate is. What do we mean? We mean that how many amounts of the H2O liquid evaporates to the H2O gaseous, the same amount backs to the liquid at the same rate and the equal rates, guys. So simply this is the vapor pressure, a pressure exerted by the vapors which collected on the surface toward the surface, but the system should be in equilibrium with the liquid phase as well. Let us answer the question that if we compare the solvent, pure solvent, and the solution's vapor pressure, which one will provide more vapor pressure? Guys, have a look on this figure. It's figure 7. first represents the pure water. We do not have any impurities. The second represents an aqueous solution of a non-electrolyte solute or non-volatile solute. Have a look there, guys. We do not have any solute impurities to be a barrier in front of the water molecules to escape. So the 1, 2, 3, 4, and so many vapors are existing. Why? Because guys, also the vapor backs to also to the liquid. Why? Because here in this process there is no barrier in front of the water molecules to escape and vaporize into the surrounding. And here, as you can see, that we have a high amount of vapor. But in the solution, due to having solute molecules, guys, the solute molecules, they attract to the solvents. They do not let the water molecules to vaporize as easy as the pure solvent. Why? Because here we have got barriers to the water molecules. The water molecule attracted by the solute molecules, so they will not vaporize as easily as the pure solvent. And as you can see, guys, here we have much lower vapors in the surrounding than comparing to the pure solvent. So low vapor in the surrounding. And this can be, a statement can be stated that the vapor pressure of a solution compared to solvent always is lower and lower because of existing the solutes and attract to the solvent. So vapor pressure of pure solvent is higher than vapor pressure of solutions, regardless to the type of the solute, guys, whether it's non-electrolyte, electrolyte, or any solutes. So we have concluded that as we add more molality, that lowers the vapor pressure more. So what's the relation between concentration in molality to the vapor pressure? It's inversely proportional. As we add more solute into the solution, that lowers the vapor pressure much more than the pure solvent, and there will be a greater distance between the vapor pressure of the solvent with the solution. And in this section, guys, we will be talking about the concentration in molality rather than molarity, because the molality does not depend on the temperature, does not change by changing temperature. And as you know that molality is equal to mole per kg kilogram of solvent. And the kg is independent on temperature. But if you use the molarity is equal to mole per volume in liter, and the liter depends on the temperature and changes by temperature. So we do not use the molarity in this section. Instead, we use the molality because it's independent on temperature. So guys, we concluded two informations. First, the vapor pressure of a solution is lower than the solvent, and the vapor pressure is inversely proportional to the concentration in molality. Here I have answered the question why the vapor pressure of the solution is lower than the solvent. Guys, we have two non-electrolytes here, two different non-electrolytes, glucose and sucrose. In this part of the colligative properties, at the beginning we'll be talking about non-electrolytes, and later in the second part of the colligative properties we'll be talking about electrolytes. We will include the electrolytes as well. Guys, the glucose and sucrose, they have different properties, identities, but as we add 1 molar of glucose into water and 1 molar of sucrose into water, they lower the vapor pressure by the same degree, by the same amount, which is 5.5 10 to the power minus 4 atm. So 1 molarity lowers the 5.5 10 to the power minus 4 atm. 2 molarity twice, 3 molarity triple, 4 molarity fourfold, and so on. That represents, regardless to the identity of the solute, the vapor pressure lowered. Depends on the concentration. That's why this is the evidence the vapor pressure is a colligative property, because the colligative properties, they depends on the amount, concentration, not on the identity. When a vapor pressure is lowered, the solution remains liquid over a large range of temperature, guys. As the vapor pressure reduces, the solution stay as liquid rather than to be gaseous or to be vapor for a larger range of temperature. And we have two relations, guys. The vapor pressure is inversely proportional with the molarity, as I have written above. But the vapor pressure lowering, I will define what we mean by vapor pressure lowering, is directly proportional to the molarity. So in vapor pressure, we have to know these two relations. What will happen to the vapor pressure by molarity? It's inversely. What will happen to the vapor pressure lowering by molarity? Guys, what's the vapor pressure lowering? Vapor pressure lowering. We said the solvent and the solution, they have different vapor pressures. And the vapor pressure of the solvent is higher than the solution. Guys, as we add more solute, for example, the solvent, suppose that the solvent, its vapor pressure is 1 atm. Suppose that, this is a supposed suggestion, guys. Just suggest that we have the 1 atm. 1 molarity of sugar, 2 molarity of sugar, 3 molarity of sugar will reduce the vapor pressure by that number, 5.5 10 to the power minus 4 atm, will reduce it. And then 2 multiply 5.5 10 to the power minus 4, and then 3 multiply 5.5 10 to the power minus 4 atm. As you can see, guys, the lowered value, the degree of lowering, as we increase the molarity, the vapor pressure lowered much more. And the distance, the difference between the vapor pressure of the solvent and the solution becomes more, higher. So the vapor pressure lowering represent what? Represent the difference between the vapor pressure of a solvent with its solution, where it is solution, guys. So the vapor pressure lowered, but vapor pressure lowering, the difference becomes more as we increase molality. That's the vapor pressure lowering, represent the difference between the vapor pressure of the solvent to the solution. Guys, let us solve this question, simple. Which one has lowest vapor pressure or lower vapor pressure? Of course, vapor pressure is inverse with the molality. The one that has lower vapor pressure must have the highest molality. So A is the correct answer. But if it requires the vapor pressure lowering, the one with the lower molality has lower vapor pressure lowering. So, highest molality is equal to the highest vapor pressure lowering and equals to what? Lowest vapor pressure. This is the relation in order to answer such questions, guys. The lowest, if the lowest vapor pressure is required, choose the highest concentration. If the highest vapor pressure lowering is required, choose the highest molality. And also for the lowest concentration, choose the, if it requires the highest vapor pressure, choose the lowest concentration. The lowest vapor pressure lowering, the lowest concentration. This is all about the vapor pressure, guys. We do not have mathematical questions for the vapor pressure. We have in reality, but in our curriculum, it's not included. The second colligative property is the freezing point depression. So from the term of the depression, we mean that as we add more solute, the freezing point depressed more or lowered more. Guys, said that when we have two solutions, or a solvent with a solution, solvent, pure H2O. And here we have got H2O with the solute, we mean the solution. The blue spots represent the solvent and the red spot the solute. Solution. If the pure solvent is H2O, it has a freezing point of 0 Celsius. 0 Celsius. It freezes at 0 Celsius. But guys, what do you think about the freezing point of the solution? If you notice that as the solute added, there will be attraction between the solute and the solvent. And existing the attraction between the solute and the solvent does not allow the solvent or the solution to freeze at the same degree as the solvent, as the pure solvent. There we do not have any impurities. Freezes at 0 Celsius. And we have this statement, as we add 1 molarity of a non-electrolyte solute, non-electrolyte means sugar and alcohol, guys, said it lowers the freezing point by minus 1.86 Celsius. But prior to write the amount, I want you to understand why the freezing point of a solution is different than the solvent. Because in the solvent we do not have any impurities to attract to the solvent, and then it freezes, it is normal temperature. But the solution, the solvent attracts to the solute, and it has no tendency to freeze at the same degree. Otherwise, we have to lower the temperature much more to freeze the solution. and by adding one molality, it has a freezing point of minus 1.86 Celsius instead of 0. And to molality, it has twice as that, which is minus 3.72 Celsius. 3 molality, it is 3 times 3 powers that, minus 5.58 Celsius, and so on, guys. So as we add more solute to the solution, what happened to the freezing point of the solution? Lowered more. We can conclude that the freezing point of pure solvent is higher than the freezing point of solutions. This is the first conclusion. It's the same to say we have got 0 Celsius. Let me show you on the coordinator, guys. Adding 1 molality will lower it to minus 1.86 Celsius, then minus 3.72 Celsius, then minus 5.58 Celsius, and so on. Here we have added 1 molality of a non-electrolyte, 2 molality, 3 molalities. Guys, note that, let us conclude another relation. As we add more molality, so as molality increase, what happened to the freezing point? Becomes much lower. So the freezing point lowered. And we can conclude another relation that the freezing point, guys, is inversely proportional to the molality, which is the concentration. But we have another term, as we had in vapor pressure and vapor pressure lowering. Here we have freezing point depression. What do we mean by freezing point depression, guys? Freezing point depression is the difference between the freezing point of the pure solvent and its solution, and the solution of the non-electrolyte that contain non-electrolyte non-volatile solute. So when we have differences between the freezing point of the solvent with the solution, this is first, second, and third. And the freezing point depression, guys, in our book represents by delta TF. Delta TF. Delta TF means change in freezing point between the solvent to the solution. Let us derive another relation. Guys, what happens as the molality increase? What happens to the, for example, A, B, C? What happens to the freezing point depression delta T, delta TFA, delta TFB, delta TFC? As molality increase, the delta TF also increases too. So as molality increase, the freezing point decrease, but the freezing point depression increases. The second relation can be stated: freezing point depression is directly proportional with the molality. Directly proportional with the molality. And for the freezing point, guys, we have a constant unit, a constant value, we call as the molar freezing point constant. What's a molar freezing point constant? You can notice, guys, for increasing one molality, the difference between the freezing points, the difference between each freezing point is equal, and for water is equal to minus 1.86, minus 1.86, minus 1.86. We mean minus 5.58 minus 3.72 results in minus 1.86. And between 186, 372, there is 186. Between 0 and 186, there is 186. This constant changing of freezing point by 1 molarity difference we call as the molar freezing point constant. So is a freezing point depression of the solvent in a 1 molar solution of a non-volatile non-electrolyte solute. And that value for water must be memorized. We'll be talking about it in detail, but I want you to understand the Kf, which is the depression, constant depression for 1 molar of a non-electrolyte non-volatile solute. How to calculate the freezing point, guys? For the freezing point and boiling point, we have calculations, mathematical questions. We have got two equations for delta TF in order to calculate. One depends on the Kf and molarity, one depends on the freezing point of solution and solvent. So the first equation, guys, is what? Is the freezing point of solution minus freezing point of solvent. This can be used when you want to calculate the freezing point of solution through the delta TF or delta TF through the freezing point of the solution. And guys, if the solvent is H2O, delta TF equals to the freezing point of solution. Why? Because the freezing point of solvent will be 0, and then this equalizes delta TF and freezing point of a solution. The delta TF, the second equation, guys, equal to Kf multiplied molarity. Kf, which is the molar freezing point constant, multiply the concentration. The Kf expresses in Celsius per molarity, and the M expresses in kilogram, the mole of the solute per the kilogram, the molarity, and the delta TF represents by or has a unit of Celsius. Guys, Kf for H2O must be memorized. Only Kf of H2O, the other solvents are not required to be memorized. It should be given for the questions. It's minus 1.86 Celsius per molarity. So we concluded the freezing point is inversely with the molarity. Which one has lower freezing point? Of course, the higher molarity. Freezing point depression is directly proportional with molarity depressions. Which solution has lower freezing point depression? Lower freezing point depression must be lower molarity, so 2 molar of glucose instead of 4 molar. So guys, whenever there are two types of questions, asking for the highest or lowest freezing points, or mathematical questions, the second type. Whenever asks for the highest and lowest freezing point, the highest M, this is for non-electrolyte, guys, is the same as lowest freezing point and is the same as highest delta TF, freezing point depression. But the lowest molarity, guys, lowest M, is the same as the highest freezing point and is the same as the lowest delta TF. These two statements can be used to answer the questions of which of them has highest freezing point, lowest freezing point, highest freezing point depression, lower freezing point depression. Let us practice some questions, guys. Here we have practice in page 21. The mass is given, the amount of the gram. So it's what? 10.3 grams. The other quantities which are given, the mass of the H2O, but it's in the gram. So guys, you have to convert mass of solvent to kilogram always. You have to convert the mass of the solvent to kilogram always, but mass of solute stay unchanged. So do not convert the mass of the solute, it must be in gram, and usually it provides in gram. It requires the freezing point depression. Guys, in order to calculate the freezing point depression, delta TF is equal to Kf multiply M. The Kf should be memorized. The delta TF is a requirement, and how to find M? Guys, M is equal to mole of the solute divided by kilogram of solvent. And the kilogram of solvent is given in gram, 250 grams, should be 0.25 kilograms. And instead of mole, we can use the mass and molar mass. Mass per molar mass. The mass, which is given 10.3 grams, divided by the molar mass, which should be given always 180 gram per mole, and divide by 0.25 kilogram. This results the molality, which is 0.229 molar. 0.229 molar can be replaced here to solve the question and multiply by what? By minus 1.86 multiplied by 0.229 results the freezing point depression, which is minus 0.426 Celsius. More questions, guys. In a laboratory experiment, the freezing point of aqueous solution of glucose is found to be minus 0. This should be O, guys. I have stated here O. Minus 0.325 Celsius. What's the molar concentration of this concentration, or in this solution? Delta TF, guys, is equal to Kf multiply M. And the M is equal to delta TF divided by Kf. And the Kf is given, well, we have to memorize it, 86, by the delta TF, guys. If you remember, I told you, I said whenever the solvent is water, the freezing point depression is equal to the freezing point of the solution. So here the freezing point of aqueous solution is given, minus 0.325. We can say directly this equal to the delta TF. Why? Because the solvent is water and it has got the same freezing point depression as the freezing point of the solution. And minus 0.325, we can divide these two numbers to get 0.175 mole. More questions, guys. If a 0.5 molar of non-neutralized solid are dissolved in 500 grams, so this should be 0.5 kg. Change it. And the mole is given direct. What's the freezing point of the solution? Guys, delta TF is equal to freezing point of solution minus freezing point of solvent. And as you know that the solvent is water, is ether. So here the freezing point of solution is not equal to the delta TF. We cannot say, because the ether has different freezing point than 0. How to solve for it? First of all, try to find delta TF, which is equal to what? KF multiply M. The guys, how to calculate the M? Here we have got the minus 1.79 Celsius per molarity, which is the KF of the ether. And we calculated the molarity by what? By dividing the 0.5 mole to the 0.5 kg, so results 1 mole. We use the molarity here, and the KF of ether must be given, guys, minus 1.79 Celsius per molarity, so results a delta TF of minus 1.79 Celsius. When we know the delta TF, and also we know the freezing point of a solvent, which is given here, the ether, will you be able to calculate the freezing point of solution? Yes, of course. So let us calculate the freezing point of the solution. The freezing point of solution is equal to the delta TF plus freezing point of solvent, because the freezing point of solvent must be taken to the other side. So guys, the freezing point of a solution here we have done. Take to there, it will be positive freezing point of solvent, and then negative multiply negative, it's positive. When you take to the other side, will be negative, and plus 1 minus 179 results the minus 118.1 Celsius, which is the freezing point of the solution. More questions, guys. The freezing point of an aqueous solution that contains a non-electrolyte is minus 9 Celsius. What's the freezing point depression? So guys, when the freezing point of a solution is given, and the solution, usually if the solvent is not given, we mean the solvent is water, and delta TF is equal to minus 9. Why? Because it's the same as the freezing point of the solution. And what's the molar concentration of the solution? Of course, M is equal to delta TF divided by KF, and is equal to the minus 9 divided by minus 1.86, and results 4.84 mole. Let us talk about the third colligative property, which is the boiling point elevation, guys. The boiling point elevation, in order to understand how it changes with concentration, let me provide an example. Guys, when we want to understand the boiling point, suppose we have got two containers, and the first one only pure solvent, and the second one is a solution. The solution contains solute, and in this part we are talking about the non-electrolyte solutes. Guys, if it's H2O, H2O has a boiling point of 100 Celsius. But let us compare the solvent to the solution. As we add more solute, there will be more attraction, or there will be existing attraction between the solute and the solvent. And as the solute and the solvent attract, we have to provide more energy to break the attraction and let the molecules of water to boil, or the solution to boil. And providing more energy, we mean that we have increased the temperature, or we have increased the boiling point of the solution. So we can say simply that the boiling point of solutions, the boiling point of the solutions higher than the boiling point of solvents. Unlike the freezing point and vapor pressure, the boiling point of solution is higher than the solvent, not the solvent higher than the solution. This is the first statement. The second, how the boiling point changes. Suppose we have a coordinator here, and this is 100 Celsius for H2O. We have a statement as we had the Kf for the freezing point. We have Kb, guys, Kb for the boiling point. Said when one molarity increases, the change or the elevation will be by 0.5. So here we have 100.51, 1 molarity. 2 molarity increase twice, 101.02, something like that. 3 molar, 101.552 or something like 53. And so on, guys. So let us draw a relation between the molarity and the boiling point. As you can notice that as the molarity of the solutions increase, what happens to the boiling point? Increases too. So let us say that the molarity is directly proportional with the boiling point of solutions. We have a term with the molarity, with the boiling point, guys. The boiling point elevation. What do you mean by boiling point elevation? As we had freezing point depression, it was the difference between the freezing point of solvent and solution. The boiling point elevation is the difference in boiling point between the solvent with the solutions, between the solvent with the solutions. And as you can see that, guys, what happens to the difference as we increase molarity? And the boiling point elevation represents by delta TB, guys. Delta TB of A, delta TB of B, delta TB of C. The one with the higher molarity has a higher delta TB. So the second relation is what? Is molarity is directly proportional with the delta TB. We can say that molarity is directly proportional with boiling point and boiling point elevation as well. With the molarity, guys, by changing every molarity, the degree temperature, the boiling point changes equally. The elevation in boiling point for 1 molar non-electrolyte solute represents the Kb of the solvents. So the Kb is what? Is molar boiling point constant. It represents the elevation in boiling point for 1 molar of a non-electrolyte, non-volatile solute, and here the difference is 0.51, 0.51, 0.51. This elevation for 1 molarity is the Kb of the solutions. And we have defined the Kb, the boiling point elevation of a solvent in 1 molar solution of a non-volatile non-electrolyte solute. And the Kb for water must be memorized, which is 0.51 Celsius per molality, guys. As we have two equations to calculate the delta TF, we have the same two equations for delta TB, but instead of using the freezing point, we use the boiling points. The boiling, this is the first one, guys. Delta TB, it must be boiling point of solution minus boiling point of solvent. And the boiling point of solvent is 100 Celsius usually for water. And the delta TB equal to Kb multiplied molarity, the second equation. The molarity of the solutions. Guys, we have to know that Kb and Kf values, they change only with the solvent. So what changes the Kb and Kf? The solvents. What is the evidence that the solvent changes the Kb and Kf? Here we have several solvents. And the Kb, Kf, and with the Kb is given. As the solvent changes, there will change in the Kf and Kb as well. So the Kb and Kf depends on the solvents. As the solvent change, that changes the Kb and Kf. Three informations for water must be, or four informations for water must be memorized. Its boiling point is equal to 100, you know, guys. The Kb is equal to 0.51 Celsius per molality. The freezing point is equal to 0 Celsius. The Kf, molar freezing point constant, is equal to minus 1.86 Celsius per molality. These four informations must be memorized about the water, which is the solvent that we frequently deal with. We said the boiling point and boiling point elevations are directly proportional with molarity, so let us answer the question, which one has the higher boiling point or boiling point elevation? The higher boiling point or higher boiling point elevation, 0.52, so the second molarity. So guys, use this to answer the questions of the first type questions. Highest molarity represent the highest boiling point and highest boiling point elevation, delta TB, sorry, B small. So highest molarity, highest boiling point, and highest delta TB, which is the boiling point elevation. Lowest molarity, lowest boiling point, and lowest delta TB as well. Let us solve questions we have practiced in page 22, guys. A solution contains 50 grams of sucrose. It's non-electrolyte. 500 grams of water must be converted to kilogram. What's the boiling point elevation? Boiling point elevation is delta TB is equal to Kb multiplied M. We know the Kb, it's 0.51 Celsius per molality, and multiply the molality. The molality equals what? The mole, and the mole we do not have directly, is equal to mass. Mass 50 grams is given. Divide by the molar mass of the sugar is what? The 342 grams per mole. The sucrose has a molar mass of 342 grams per mole, and then the molar mass of the mass of water is 500, it will be 0.5 kg. That will be the molality, and multiply this by the Kb, you'll get the value of 0.15 Celsius. One more question, guys. The mass is given, mass of the solute, and the mass of the solvent, the same strategy. we calculate the molality. The molality multiplied by the KEB gets the delta TF or delta TB, sorry. And in order to find the delta T, the boiling point of solution, of course, is equal to what? Delta TB plus boiling point of solvent. And the delta TB is 2.7 plus the boiling point of the solvent, which is 100, it will be 102.7 Celsius. Guys, in this question, if the boiling point elevation of an aqueous solution contains a non-volatile non-electrolyte is 1.02, this is delta TB. Delta TB. What will be the molality? M is equal to 102 divided by 0.51, so it's almost 2 molar. That's the solution. The boiling point of an aqueous solution containing a non-volatile non-electrolyte is what? Is 100. This is boiling point of solution. What's the boiling point elevation? So delta TB is requirement is equal to boiling point of solution minus boiling point of solvent. The boiling point of solution is 100.75 minus 100. You'll get 0.75 Celsius. This is delta TB. What's the molality of the solution? Divide this by 0.51. You'll get the molality, because divide the delta TB by KB, 1.5 molality is the answer. Guys, for the solutions of the questions, there will be several ideas of the questions. So whenever something is given, try to convert to the molality and the KB, KF as given, then you will be able to solve the questions. Sometimes, guys, the freezing point of a solution may be given and asking for the boiling point of the other solution. Let me solve a question like that, guys. If freezing point of C6H12O6 is a solution is minus 2 Celsius. Find the boiling point of that solution. Guys, how to use the freezing point to calculate the boiling point? Of course, the molar mass must be given. First of all, try to write what's the requirement boiling point of solution. Guys, delta TB is equal to boiling point of solution minus boiling point of solvent. Okay, we have this is 100. So in order to calculate this, we have to try to find delta TB. And for this, we have got another equation of delta TB, which is equal to KB multiply M. We have got KB, 0.51, but we don't know M. By using the freezing point of the solution, try to find the M of the solution. So we have this equation, delta TF is equal to KF multiply M. And the freezing point of the solution is minus 2. And if you remember, I told you, whenever the solvent is water, the freezing point of solution and the delta TF are equal. So here M is equal to delta TF divided by KF, and the delta TF is the same as the freezing point of the solution, minus 2 divided by minus 1.86, equal to a value, guys, 1 point something, okay? 1 point something, anything that I have no calculator to calculate it. X, this is the value of the molality. And if you calculate this molality, take the molality to here, the X, multiply by 0.5, you'll get the delta TB. And if we calculate the delta TB, take the delta TB to here to calculate the boiling point of the solution. So for example, delta TB is equal to 5, for example, 5. And how to find the boiling point of a solution? This is 100. Take to the other side, it will be minus 100, it will be 100. So the boiling point of solution at that time, it will be 105 Celsius. That's how we can use the freezing point to calculate the boiling point, or the boiling point to calculate the freezing point. Doesn't matter, it has the same strategy. The last colligative property, which is the osmotic pressure, guys. In order to understand the osmotic pressure, first I would like to show you this figure, and I will explain all the terms on this figure, guys. Suppose we have a YouTube. This is a YouTube, guys, and the YouTube has a site has a pure solvent or a low concentrated solute. It can be pure solvent or low concentration, both possible, but in this case it's pure water. And the other side with the high concentration, high M, high molality. As you can see that in this side we have got solute and the solvent, but this side, the other side, only pure water. And the other side can be also low concentrated. And you know that whenever there are two solutions, or a solvent with a solution with different concentrations, there will be movement of particles. What movement of particles, guys? Through what? As you can notice here, we have got a membrane. Let me enlarge the membrane here to explain what's the function of this membrane, how it works. Guys, this membrane is a porous membrane. We mean it has pores. And the membrane has a function that allows the passage of the small sized particles as the size of the pores, but blocks those particles which have the higher size than the size of the pores. So for example, for a door, a human being can pass through a door. Why? Because the size of a human being is smaller than a door. But an elephant or a truck cannot pass through a door. Why? Because the size of the truck is much larger than the size of the opening. So the function of the semi-permeable membrane, this membrane we call as a semi-permeable membrane, it refers to what partially allows the passaging, the movement of the particles. So this is a semi-permeable membrane. A semi-permeable membrane has a function that allows the passage of solvent which has smaller size. As you can see that the size of the solvent is much smaller than the size of the solute here. Compare these two, you get the difference. But block the passage of solutes. So the solute cannot pass through this membrane. A semi-permeable membrane is a membrane that separates the two solutions or the pure solvent with the other solution from each other first. Second, it allows the passage of the pure solvent but does not allow the passage of the solute. This is a semi-permeable membrane. The part A, this figure, guys, is before the osmosis, guys. So let us, yeah, let us talk how the osmosis happen and what can be applied to stop the osmosis. As you can notice, guys, the movement of the particles of the water from the low concentration side or the pure solvent to the high concentration side is much than the movement of water from the high concentration side to the low concentration side. We have to know that there will be movement of water from the low concentration to the high concentration, and as well from the high concentration to the low concentration. Only water can pass through this semi-permeable membrane. But due to that, the movement of the water from the low concentration side to the high concentration side is much than dominated over the movement from the high concentration to the low concentration side. There will be the movement of water molecules toward the high concentration site much more. And this movement will produce, we call in chemistry as osmosis. So the osmosis is what, guys? Osmosis is the movement of solvent from high concentration side, or we can say low concentration side toward the high concentration side. And the movement of water predominates from the low concentration or the pure water toward the high concentration over the movement from the high concentration toward the lower concentration. And this movement continues, and as you can see in the first part A, we have equal levels of the two solutions, or the pure solvent with the solution. But for the part B, we have different levels, guys. This is a height, h. What causes this difference in level or elevates the high concentration side and lower the low concentration side? The osmosis. And in order to stop the osmosis, we have to apply an external pressure. The external pressure must be applied. And that external pressure we call as the osmotic pressure. Osmotic pressure, guys. We call as what? The external pressure we call as the osmotic pressure. And the pressure toward the high concentration side we call as the osmosis. The osmosis exerts the pressure toward the high concentration side and elevates the level of the high concentration side. In order to stop the osmosis, we have to apply an osmotic pressure, and the osmotic pressure must be applied externally to stop the osmosis. And as the osmotic pressure applied, there will not be movement, or we can say that the movement of water from the low concentration side or the pure solvent toward the high concentration side will be equal to from the high concentration side toward the low concentration side. As you can see here, guys, the movement of the two water molecules from the low concentration side goes to the high concentration, and two water molecules back at the same time. So this results a net movement is equal to what? Zero net movement. The net movement is zero. What I mean? We mean the movement, there is still movement, guys. It's continuously the water moving past through the membrane, the semi-permeable membrane. But with equal rate is from the high concentration toward the low concentration, and from the low concentration toward the high concentration, guys. So here we discussed about the semi-permeable membrane. We said it divides the solutions from each other. Second, and we discussed about the function of semi-permeable membrane. We said it allows the passage of small-sized particles, which are the solvent in our case, and blocks the passage of the large-sized particles because it has porous membranes. In our case, it's the solute. And then the osmosis. Osmosis is the movement of water from or a solvent from the low concentration side toward the high concentration side, and the osmosis, the osmotic pressure must be applied, is an external pressure which must be applied to stop the osmosis. In order to stop the osmosis, we have to apply the osmotic pressure. So guys, here we have got allows the passage of some particles, solvent, while blocking the other passage. A semi-permeable membrane allows the water molecules but not sucrose molecule to pass through because of having different sizes. Rate at which the water molecules leave the pure water side is greater than the rate at which they leave the solution. This causes the level of the solute to rise. And we defined the osmosis. We said the movement of a solvent through a semi-permeable membrane from the side of the low concentration to the high concentration. And osmosis occurs whenever two solutions of different concentrations are separated by a semi-permeable membrane. In order to stop this osmosis, we have to apply the osmotic pressure, and this is the external pressure that must be applied to stop the osmosis. Guys, the osmosis, as we add more solute, to the solution, there will be a concentrated solution, and as the solution becomes more concentrated, the water movement, the more amount of water moves to from the low concentration to the high concentration side. And as the amount of water moves to the high concentration side, the osmosis becomes more. And as the osmosis becomes more, the pressurizes more, elevates the level of the solution more, we have to provide a higher osmotic pressure to stop the osmosis. So, guys, molality increases, that increases the osmosis. And as osmosis increases, we have to apply a higher osmotic pressure. So what's the relation between molality and osmotic pressure? Is directly proportional. The higher molality results a higher osmotic pressure, the lower molality, lower osmotic pressure. Which of the solution has a higher osmotic pressure? Of course, 2 molar